Welcome to today's webinar. The topic today is automatic calculation of seismic displacement in response spectrum analysis. My name is Andreas Hörold. I'm responsible for marketing and public relations. For example, the German and English webinar or webinars, then the technical content of the website, newsletters, customer projects, and so on. I will be the moderator today and I will answer your questions together with Thomas Eichner. The presentation will be done by Victor Hidalgo. He's responsible for the dynamic add-ons and he works also in the customer support team. And Thomas Eichner, he's also responsible for the development of the dynamic add-ons and he works also in the customer support team. You can ask questions when you press the button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Victor. Victor, it's your turn.
Oh, thank you, Andreas, for the introduction. Now let's start with the content. So in the first place, we are gonna do an introduction to the topic calculation of seismic displacement in the response spectrum analysis. Then we are gonna see the new factor in the response spectrum definition. The third step, with an application example, we will take a look on the new subresult and its advantages. Then we will take a look in the integration of the new subresult with the building model add-on, also connected with response spectrum. And finally, we are going to talk about the future developments for the seismic displacement and for this topic in general. So let's start with the introduction, calculation of seismic displacement in the response spectrum analysis. And we are gonna use as the reference number one and the basic reference in this whole presentation. It's gonna be the Eurocode number 8, design of structures for earthquake resistance. Yeah, and as a second reference, we have a previous webinar on this topic with the title Seismic Displacement Limits and Seismic Design of Buildings in FM 6. Now, this was in the last year, November, presented by me also. And we are gonna use the model, so the application example we are taking from this webinar, and also a couple concepts that I'm gonna repeat in the next slides. But also, if you want a deeper view on the topic, you can maybe take a look on this webinar. Yeah, here's the link in the presentation that you can download after today. Yeah. In this webinar, we presented these topics, or an overview would be following topics. It's a general in the topic seismic displacement. We have in the first place the elastic spectrum and the design spectrum concepts inside Eurocode. After this, we can jump in the displacement calculation. Here you see the sections from the Eurocode 8 that define these calculations. After this, we did a comparison with the limitation of the interstory drift. So there are specified limits by the norm. We have to comply them. After that, we made a small analysis on the modeling assumptions and the specification regarding stiffness and modeling in general for seismic design. Finally, we made a procedure with building model add-on, and we explored the connection between building model add-on and response spectrum analysis. Yeah, important for response spectrum analysis. RSA is the abbreviation of the analysis, and maybe at some point I'm gonna use this small name abbreviation. Yeah, RSA. Okay, and the new feature that we are presenting today, it's a feature that is focused on steps 1 and 2. Yeah, so this new development affects or has implications in the definition of the spectrum and how to calculate displacement. Yeah? So with our philosophy, so the idea is that we have now an automatic calculation of this seismic displacement. Okay. For that, we are going to show the results on this model, but we are not going to explore that in depth. It's just a concrete model that was developed for this webinar. We are going to show a couple results on that, but not focus on the modeling. Okay. Okay, let's jump now to a short review on the elastic spectrum and the sine spectrum in these sections. So for the Eurocode 8, we have these two concepts for our curve for acceleration ordinate in the spectrum. And we have two possibilities, the elastic spectrum and the design spectrum, with the big difference that the design spectrum contains this Q letter, which has the name behavior factor. It's a description of the characteristics of the structure, yeah, regarding material and structural configuration, which can be also translated in how it behaves in the inelastic range, yeah. And let's take a quick review between this elastic and inelastic, yeah. The black line represents the elastic response of the structure, where that's the assumption of this kind of analysis. RSA is a linear analysis, and well, we can perform this analysis represented with this line. Now we know that in reality the structure is going to exhibit some degree of inelasticity. The difference between the forces can be summarized as this behavior factor mathematically, but physically it has the interpretation we say now that a description of the structural configuration and material. Yeah. So if we say that this is the difference Q between elastic and inelastic, on the forces side, maybe base shear or internal forces, then there is the question, where is the inelastic displacement, at which level, no? Because we made this division, but the difference in forces with respect to the linear and the nonlinear analysis, the difference in forces does not take place in the displacement. So in the displacement, the assumption or the base of the RSA is that for both linear and nonlinear displacement, or linear and real displacement, they are almost the same. So this area represented with this blue area is almost the same. And since I am using for calculation the so-called design spectrum, I'm using a reduced value of the forces that is not going to be compatible with the level of the displacement. Yeah, and that's the duality for the RSA analysis, and that's kind of what it's about this topic now, to calculate back the real displacements on this. Gonna show here the curve of this concept for the ASCE 7. That's the norm from, or the base norm from United States, which is like the source for all these seismic analysis. Yeah, so it's almost the same graph. Just to remark here that the actual inelastic response of the structure is something between our idealized inelastic response and the elastic response. Now we are somewhere in the middle, but we have some assumptions in the displacement where we calculate the real displacement and the elastic, that's the elastic displacement. Yeah. Okay, enough with this first topic. The second topic, the displacement calculation, the section 4.3.4 introduces the concept of Q sub D. QD is the displacement behavior factor. It's just a behavior factor plus the word displacement. And in general, it's assumed equal to Q unless otherwise specified. So this means that we are gonna take our displacement calculated according the design spectrum. So here the section 3225, which corresponds to the design spectrum. So this means the spectrum divided by Q. Yeah. And then we multiply by QD, which in general is the same value. So we are calculating back to the displacement now. So we are taking the reduced spectrum and then we are multiplying again by Q. Yeah. This approach seems kind of trivial, but we are gonna see an example where it is not so simple. Yeah. Okay. So Q or QD, we are gonna talk about this behavior factor definition. So originally this Q, yeah, and we have two examples here extracted from the reference one, so code 8, and this is simply the behavior factor definition for two materials, now for concrete and for steel buildings. We see that the behavior factor is provided inside these chapters, and it's also introduced with the word structural types, or with the concept structural types and behavior factors. So we'll see a dependency on the material, but also on the structural type. So in general, as a structural engineer, making the design process, or at the beginning, we choose one structural type of the specified in the norm, and then we work on with this definition. Of course, there can be changes with respect to basic values, but as a general rule, we come here. According to the material, we make a selection of the structural type, and that provides us with the behavior factor. Here on the right, the same for steel. And this is an example for your code, and just to provide you with the full context on how this development was done here in FM. I'm gonna show a similar example for the norm from United States, where we have a table, yeah, that as a first filter, or as a first entry on the, let's say, on the classification, we have the structural type as a big chapter. So chapter B in this case, in this example, of course, we have A, B, C, D, but so the first filter, or the first classification, better, it's the structural type, and inside the structural type we have the definitions for the material. So quite other approach, but at the end provide the same information. But the big difference is that in this table we have two coefficients, R and CD, which account are equivalent to Q and QD. Yeah. So this response modification coefficient R is the equivalent to Q, and CD from displacement is like the equivalent to Q sub D. So one can write this like Q approximately or almost like the same as R, and QD is approximately CD. Just from the values on this table, we see that the definition is not as trivial as I just said as in Eurocode, where Q is equal QD. Here we see sometimes very big differences between R and CD. No? We see here 8, 4, and also 6, 5. In this case, it's the same value, no? But we see that both values are not different. This is the approach of each norm that we had to check out and make a decision for the whole concept inside airframe. Yeah? Exactly. So in airframe we can select Eurocode or ASCE, and it should work for all of them. No? Here I'm showing these two examples, but there are a lot of examples. Maybe if it is of your interest after this presentation, you can go through all the available norms and standards in our program and check out the definition for each of them. Now there are very different approach in general in each country. Some countries are based on this North American approach. Some other are based on Eurocode, and of course there are the cases which came up with a new set of factors and nomenclature. Yeah? So it's quite a wide range of application. Okay, so let's jump now into the second part of today, and it's the new factor in the response spectrum definition. And this new factor is calculation unification for all standard groups. Yeah, I'm gonna show in the program what's exactly meant by standard groups, but it's the idea to unify this calculation for all standards in our program. Yeah. One can say that the section 4.3.4, so this displacement calculation, is included in every standard. So that's more than the standard. It's a basic assumption from RSA, from response spectrum analysis, and it's present in every norm. Yeah, maybe different other nomenclature, but it's a basic definition as itself, now intrinsic to the response spectrum analysis. And the advantage of a linear calculation, as in response spectrum, is that it's possible to make a direct multiplication from the displacement, as we saw in the first graph in today's presentation. Or as in the section 4.3.4, we have to multiply to have the real displacement, the seismic displacement. Yeah. So this multiplication from Eurocode can be generalized as a factor. Yeah, multiplying the displacement, and this factor is dependent on the standard group or the standard that we are using. Yeah. Use another remark regarding elastic spectrum and design spectrum, and in a more general way, one can say that the elastic spectrum is the not reduced version of the spectrum, and the design spectrum is the reduced version. No? And this is the approach in Eurocode and almost in the majority of the standards. Yeah? Here's an example in how it looks in airframe. So in this case, in this example, Eurocode is selected, and I can select between two categories. So the elastic being the not reduced spectrum and the design spectrum. So the reduced version. The approach might vary depending on the standard, but in general, it's almost always used as is here described now. Of course, also because of translation in the original language or particularities in each country, the words change sometimes, but as a concept remains almost the same. And our approach in RFM 6 is that the design spectrum is, of course, the reduced spectrum. Okay, and the elastic spectrum is the not reduced. Okay. Okay, so long introduction, but quite necessary. So the calculation is quite simple. It's a scaling of the results, a multiplication, but the concept behind it, it's the most important thing, and that's why so much time for this introduction. But now we see an application example, what we have now in airframe 6. As I say at the beginning, we are gonna use a model from reference 2. You can take a look on this webinar, but for today, well, it's not necessary. So we provide you with all the information. We already did the introduction. And yeah, let's take a look to this model in FM. And then we come back to the conclusion here in the presentation. Okay. So this is our building. It has several floors, and these jumps in height were done to achieve some particular participation factors in the model analysis, but it's not relevant for today. Important about this model is that I am presenting here results in the version 6, 12, 13. I'm gonna show the system information in this, just that you see what I'm talking about. So this program version is one of the last versions without the automatic calculation of the seismic displacement. So I want to show you how it looked before the new development regarding seismic displacement. So for this example, in the reference to in the other webinar, we had to use two response spectrum. One as the reduced spectrum and the other one as the not reduced spectrum. Okay. If I go to the definition of the response spectrum, we are gonna focus on the category factors. So we have the behavior factor, as we saw for the Eurocode basic definition. And once again, in the reference, the webinar in the reference 2, I show how to calculate this value. If you maybe want to take a look on a first example for it, but maybe you are experienced on the topic. So as an engineer, we make the definition on Q. We provide Q. I'm gonna change the value just here as a reference. If it's 2, so the ordinates are gonna be bigger. If it's 2.88, the previous value, so it's gonna be the definition. And here what we mentioned about elastic and design. So if I change to elastic in the category factors, I do not have any more of this behavior factor. So this elastic spectrum is the equivalent to the design spectrum, but with the Q of 1. Okay. So we have this 2.88. I'm gonna leave like the definition as before, and just keep in mind that in factors we only have these two, okay, for Eurocode. Okay. And this other definition of the response spectrum, okay, for Q 1.0. Okay, so here one additional thing in the base data in the tab standards one, according to the activation of the add-ons, I have to select design standard group, and that the definition of the standard group is the first group here. In this case, for dynamic analysis, we can select one among all these possibilities where each norm has its particular definition of the spectrum, no? But okay, so I'm gonna change just as an example to the example that we are using in the presentation as a comparison. So this ASCE7, I'm gonna change this norm. Now the definition here is according to standard. So I selected standard, and now I have another set of options. Where, for example, we have here other different approach now according to the norm. And so we see here other categories, other values, no? So quite different according to each norm, and that's why the different standards and their approach were so important in this development, no? Okay, we took a look to a version without this development, and now we are gonna jump in a recent version or a newer version where we are gonna take a look on how it looks now. Yeah, so I'm gonna go to the base data and show that for this example we keep with the Eurocode, and the help system information. This is one of the first versions with this new calculation, the 6.14.6. Exactly, so another version, and if we take a look in the response spectrum definition, we see the new factor that we already discussed in the presentation. No? So I'm gonna go inside the definition, and here let's take a look on the factors. Yeah, we have a new entry, the displacement behavior factor, where we have a drop-down list, and I select how I can define this, or how I want to define this. So the first option is that the displacement behavior factor is equal to the behavior factor, which is provided in the norm. Yeah. However, this section also has mentions that each country can redefine it according to the national annex. Yeah. And that's why we introduce this user-defined option. When I use the user-defined option, I'm able to provide a different value. Yeah. Okay. So it might be the case where we have to consider this in a different way. And this 2.88. Okay. So I'm gonna go here with the behavior factor Q, so the automatic definition, and that would be like the difference regarding for the Eurocode. So as we introduce other examples like the United States norm, let's show here what the new version of this standard is. Okay, so in this case I'm gonna go directly in the definition again. And here, this is the equivalent to the design spectrum, kind of. So it's not exactly, because you have here the spectrum type as a second category. But when I select this one, the other one it's gone. So this is a particularity. This is definition of the norm. So if maybe not that important for today, just to take a look on the factors, yeah. And when I go to the category factors, now I see that I have the two factors, R and CD. Yeah, and according to this norm, the definition, well, it's not open anymore. So there we don't provide for ASCE7 the option that it's a user-defined value, because the definition is universal, or it's constant. Yeah, so the importance factor appears with the CD value. In this case, it's already defined, and there's the section that defines it in the corresponding standard. Yeah, so that's how it would be for this norm. I'm gonna show you just one more example, just to see how diverse or how different this can be. So let's take now Canada, the 2020 version, can be also the other one. Now we take a look here to the modification factors. Here we have, in this case, the same definition as in Eurocode, for example, just by coincidence. Yeah. But here in the factors, we have now something in between. No, we have RD and R0, sub-0, which are not exactly correlated 100% to the R factor from ASCE7. So it's quite a different concept. And so use as an example, as a reference. And here we have a mixed approach where, for example, there is indeed the option user-defined. Now that the norm specifies also that according to the criterion of the engineer, this could be adjusted, or there are some other factors that could be here manually adjusted. So when I use user-defined, the factor, it's gonna be editable. No, if I come back to according 4.1.8.13 here I have the basic definition of it. If I change value, this is gonna be automatically updated. Okay, so with three examples, we see that as itself, it remains as a simple multiplication, no? Where we have, in this case, the concept displacement factor or displacement behavior factor, but the definition before, it's really dependent on the norm. It can be as diverse as one or two or three parameters. Yeah, so there is not a general rule, and each standard makes its own definition. So you have to take a look on the norm if you are switching between norms. No. Okay. So next step would be to run this model. Yeah. I already did to save some time. So this is the same model, just with results for this response spectrum analysis. So I just have already the results for this only load case. So from all the load cases, I made a run just for it. Just sake of completion, I'm gonna show here everything, the definition, or all what we saw here. Exactly. Now the results for this part. So maybe we take a look on global deformations or etc. Important here. Where do I find this new set of sub-results? For response spectrum, when we show results for a response spectrum analysis, here on the navigator, we have here a selection, according to the desired sub-result. So these rules come from the directional selected combination rule. I'm gonna show here just to have a full review on this topic. So this is the combination of directional component rule that was selected. So if I use scale zoom, the name here it's gonna change. I'm gonna leave the SRSS. I don't want to run the results again. And also we see the results per direction. So X, epsilon, Y direction, and the selected SRSS. And for sure, as you already noticed, there is a new entry, which is the combination of components of direction with the name displacement. And this is where our new factor is gonna be taken into account, and we are gonna multiply for the displacement result the base values with respect to the reduced version. So that's why the whole introduction to the topic. And now we see here in the program these results now. Just as a comparison, I'm gonna go back to the previous version, to the 6.12, and just show that the results here for this load case, for the RSA, there is no displacement entry here, so we see the difference here. Let's take once again, okay. If I minimize this, now I do see a displacement result. And that's the difference, or that's the new development. So let's go back to the presentation. And with this model, we are gonna make here a summary of what we achieve with this new sub-result. Sub-result so refers to the selection in the response spectrum. Okay, so the base size of the file, it's 3.6 megabytes. We did a version without the automatic calculation, so we need 2 RSA. So that means that in the results we are gonna have more data. And in the version with the automatic calculation, we have instead just one response spectrum analysis, but with one additional entry, So overall, of course, it's obvious we are gonna have a smaller file size, but not exactly the half, Okay. So for the first, with 2 RSA, we have a size file of 180 megabytes, and then we come down to 140. So when we talk about megabytes, it's not that relevant for nowadays capabilities of computers, but of course, if we add to this the design of the material and real example, we can really save space, and also the switching between results in the interface. So what you can do here, for example, by showing the results, let me show exactly here the selection or jumping between load cases. This is gonna be always faster if the size of the file is smaller, okay? If the file is smaller, so my computer is gonna work just better, So advantages of this a new subresult. The displacement subresult is we saw, okay, smaller files, a faster interface in the program. Also a unique load case definition, yeah, so that's also quite important. And it's automatic, it's not activable, so we made the decision to not make it optional because it's a requirement that takes place in every standard. So it's quite important that we as a software provide our customers with the best guidance possible. Yeah, so that means that we report this result, and we expect that you as a user, you wonder, you ask, what's this result, and take so I look into it and decide if it's important or relevant for your analysis and design. Okay. Okay, with that, we are done with the basic or with the biggest part of the result, and now we jump in the last part of today's webinar, which is the integration of the new subresult with the building model add-on. Yeah. Okay, so the building model add-on and the spectral analysis, or the RSA, they have when both of them are activated in the program, they deliver a particular set of results, which are the results by stories. I'm gonna show this in program, but let's take here a look to a concept. So, okay, we have this table, and this table, or this entry results by stories, have four other tables, yeah, or tabs, yeah. These tabs regarding the displacement or the seismic displacement, these interstory drifts and sensitivity coefficients, they both are gonna be affected by the selected subresult. Yeah? So at the end, we show this table for a particular subresult, and we are gonna take a look on this in the program. But let's review what these two tables do. So the interstory drift. Here's the section for the Eurocode. This is a unique definition, and as we saw, it's just the reduced displacement times the factor. Yeah? There's nothing that much to decide. No, this is a unique definition for all standards. Yeah, but there is a particularity in the sensitivity coefficients table. Yeah, this is according to the standard. We might have to switch between subresults in the spectral analysis. And here an example. So according to Eurocode, in the section 4.4.22 subclause 2, how to evaluate the so-called sensitivity coefficients is shown here. So it's the vertical load it's taken into account, and at the end, the dependency here, or the most important dependency here, or the most important parameter here, is the dr, where dr is in accordance with the section 4.3.4, which is the seismic displacement calculation. No? So here we are saying, or Eurocode says to us, you have to use this seismic displacement level to calculate the sensitivity coefficient, which so we can summarize this as a sensitivity coefficient as a function of the seismic displacement. Yeah. Now, once again, our comparison standard for today, we are going to take a quick review on the ASCE 7 and section 12.8.7. So let's take a look now what how the sensitivity coefficient is defined. Yeah. Just as a summary, I'm gonna show here just graphical example or a graphical reference, sorry. In this case, this standard defines the sensitivity coefficient based on reduced displacement. Yeah, so it's quite a particular approach, but well, it's what the standard defines, and we have to follow it now. So here we are on two levels for the same norm, so related to our new subresult and our seismic displacement concept. So for this, for Eurocode, we should use one particular subresult, and for ASCE, we should use another subresult. Yeah. Just as an extended review on this, which is just an image from this standard, and take a look on this corner. So zoom in. The subindex E defines elastic, yeah. So they're reduced, and without subindex we have the real displacement, yeah. And we see in the definition kind of this theta, the same formulation of the Eurocode here, but just that this drift, this delta, it's drift, it's referred to the E result, so to the elastic, so the reduced value, yeah. Yeah, that's also confusing. This norm uses elastic, which is not completely elastic as in Eurocode, and well, it's quite confusing, but just wanted to show as a reference what's all behind this concept. Now it's at the end a simple multiplication, but behind that there is a full concept, a full definition, that it might appear simple, but it's really important that if it's the case that you have to use another norm, combine or compare them, be careful what's the definition of each concept inside the norm. Okay, so as promised, I'm gonna switch to our model with the seismic displacement here. So I'm gonna switch to this subresult here, and I'm gonna show this table that it's only active when we have the building model add-on. Yeah. Oh, sorry. So I'm going here in the table to the spectral analysis. Yeah, and then I select this entry, resolved by stories, and for that I have to run the analysis with the add-on building model. Now here is where I can activate it, and if I select that resolved by stories, we are gonna get what I had in the presentation, which is inter-story drift and sensitivity coefficient. Yeah. So for inter-story drift, just as an example, if I show this with the subresult SRSS, so this would not be the real result. No, these are smaller displacement. These are the reduced displacement. And the subresult displacement would be the true result for this table. Yeah, but this is quite the same for all standards. But going to the sensitivity coefficients, yeah, in this case, if I'm using the Eurocode, yeah, as a standard here, it's dynamic analysis. Then I can use these values directly, but if it would be the case that I'm working with ASCE 7, yeah, then in this case, for evaluating the sensitivity coefficient, I should change to the not scale displacement. So I should use this in this case now. Of course, just as a reference, no? if in this case we are partially there because this is the result, yeah. Used for the spectral analysis, if I would like to use this in a result combination on final result, I have to consider the vertical load cases, yeah. So for this, I would go to a result combination and create an appropriate result combination. No? I can do this. In this case, I do not have, of course, in purpose, just to show you how to define it quickly. Maybe you already know, but just as a reference. So I can go to a design situation, create a new design situation of type seismic, where it's important that in the options, the combination wizard is set as result combination. Otherwise, I cannot consider my response spectrum analysis. And in result combination, the program, after jumping in the table or in the tab, sorry, we get already, according to the selected norm, the corresponding result combination. In assignment, we are gonna see the subresult, yeah. This subresult must be activated here. So just take a look in options in the base load cases and combinations. You have to activate the subresults option, and that's why I can see this column. In this case, if I want to use these results for the, for example, concrete design, yeah, I can use this directly. But if I want to maybe take a look on the displacement, so I can copy this, but then I have to use the subresult displacement, yeah. And that's so an advantage of this new development. So with the same load case, which I have only one now, one response spectrum, and with result combinations, I can create what I want to use either for design, yeah, like without multiplying, or the results in the displacement. Of course, Eurocode is directly in the multiplication Q sub D, but we saw an example from ASC7 where the multiplication factor is not exactly as the division factor of the spectrum, no? So that's why each standard has a different approach. Okay, I think that's so all on the side of content and this new development. So let's go back to the presentation just for a final word on what are the future developments on this topic, seismic displacement. As I just did in the program, I create a result combination for the seismic displacement, and each standard defines how the vertical load should be combined with the seismic displacement. So we need here an appropriate serviceability design situation for the seismic case. No, we still do not have this, and this would be the first step on this topic, future development, to create the appropriate design situation. And the idea is that the program selects automatically the corresponding subresult. Yeah. On the second part, this was not treated today, as itself, but it's you can take a look this on our reference too on the other webinar from the last year. It's the inter-story drift limit. So we want to have in the program the possibility to compare limits, directly inside the program, according to the norm, So these drift limits are specified in each standard, okay? And a final step that we consider here is the correlation between the new subresult and the table. Okay, their story drift, it's clear as we saw, but the sensitivity coefficients are a quite particular topic. We need to make, or we want to make an adjustment between the subresult and the sensitivity coefficient according to the node. So this might change for each standard, yeah. As we saw the example in the previous slide, with the standard from United States. Okay, of course, as it was the idea in the whole presentation to show this norm from United States, is for you to keep in mind that behind this there is a dependency on the standard. Yeah, maybe for one standard a definition might seem trivial, but for other standards it's quite complex. Okay. Yeah, I think so. That was from my side. I say thank you to you. Thank you for your attention, and I hope you to see your attendance in the next webinar regarding this topic. Okay, so thank you very much, and I give the word back to Andreas. Okay.
Thank you, Victor, for your presentation. At the end of the webinar, I have additional hints for you. For example, our online courses. There's the FM6 course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with FM6. Then the Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. The Eurocode 8 course for the earthquake design. And the AI Masterclass course. For more information, just click at the links here or scan the QR codes. You can get an FM6 course or an Eurocode course for free when you submit your customer project, and we will publish it. Just click at the links here or scan the QR code. And the courses are valued at 199 to 399 euros. You can also write me an email, and I will answer you what files I need for the publishing. Then a hint to our free online services. Now there's, for example, the Dlubal community. You can ask questions there, and our support team or our community members will answer you. Then with the geozone tool, you can determine wind, snow, and earthquake loads. You can, for example, download 3D models as a template for your project. You can download the free trial versions of FM6, RSTAB 9, R-Wind3, or R-Section. Yeah, and you can explore our online services when you click at the link here or scan the QR code. Yeah, you can find more information on our website, dlubal.com. For example, the recorded webinars. You can ask the AI assistant Mia all the time, 24/7. Yeah, just try it. Okay, that should be also all from my side. I thank you for your attention. Thanks again to Victor for your presentation. Thank you, Thomas, for the help by answering the questions. I wish you all a nice rest of the day. Bye-bye.